Hi everyone, so I'm going to present a short tutorial about SPAN and AVISPA tools that are designed to verify cryptographic protocols. So I will first introduce some basics about cryptography and protocols, and then I will say a few words about what we are going to formalize using the Dolev and Yao model. Then I will show you how to formalize protocols using SPAN and AVISPA. Then we will design a simple protocol using this tool, and I will present some other examples. And in fact, in order to be able to do the formalization stuff, I will need to download a SPAN and AVISPA tool. So in a Google form, you can just type SPAN and AVISPA, and you will get to this page. And there you can just go to the download link where you can download a VirtualBox disk. So you just do this, and then I will go back to the slides while it is downloading. So let's continue by basics about cryptography and protocols. So in 3 slides, so we will just need some messages. So let M1 and M2 be messages. We'll need keys, cryptographic keys, and some agents. So let A and B be agents. So using this, we can define the message composed by M1 and M2, which is just M1, M2. The message M encrypted by key K, which is denoted using brackets in this way, and the fact that A sends to B the message M. Here we have the intruder, I, that impersonates A to send the message M to B. So I acts as A to send the message M to B. Now the opposite is just that the fact that the A sends to B a message M, but it is intercepted by the intruder I. About keys, so we have got a symmetric encryption where the public key A, for instance, is the public key of the agent A, and it is supposed to be given to all agents. On the opposite, the private key KA-1, the inverse of the public key A, is only known by A. And so to decrypt the message M encrypted by KA, it is enough to decrypt using the private key, and you obtain M. And by notation abuse, we also use the same thing for the message M that is encrypted or signed using the private key KA. So once you have got this message, you can just decrypt it using KA and get M. Okay, about symmetric encryption. So the property that you have is that you have not keys for each agent, but keys for pairs of agents. So for instance, here you've got a key KAB that is shared between A and B. And another property that the decryption key is the same. You can decrypt, in fact, any message that is encrypted by KAB using the same key, and you obtain M. The properties associated to cryptographic functions are the following. So first, you've got confidentiality. So if you cipher, for instance, a credit card number using the key KB, which is the public key of B, then the agent B is the only one that is able to decrypt it, because he's the only one that owns the inverse key KB-1. You can do the same kind of thing using symmetric keys. So for instance, if you want to send this very critical receipt to someone, you can cipher it using the private key KAB if you are A and you want to send it to B, for instance. For message authentication, what we also call electronic signature, so assume that I want to prove that my email address is this one. I can just put it in clear and then encrypt it using my private key, and then when another agent receives it, he can just use my public key and check that he obtains exactly the same thing as this string. And since I'm the only one able to build this message, it's a proof that this is my email address. And of course, you've got message integrity, which means that if you've got this message, the only way to modify the content M is to know the key K. Okay, so there are some properties of cryptographic protocols. You've got secrecy, authentication of message, authentication of agent, freshness, contract signature, fairness, anonymity, and so on. We will only speak about the first one. So, a few definitions. So, secrecy, about the secrecy property. So, a protocol ensures the secrecy of a message S if an intruder cannot syntactically deduce S. This is, in fact, a property that is also known as weak secrecy. So what it means is that a message is secure if an intruder just getting all the messages he can, using all the keys he knows, cannot obtain exactly the message S in clear. Message authentication. So an agent A authenticates a message M if A knows which agent has built the message M. A stronger authentication property is agent authentication. An agent A authenticates an agent B if, after a successful session of the protocol, A knows that he has run the protocol with B for sure. And freshness is another property saying that during a protocol session, a message is fresh if this message has specifically been built for this protocol session. So we're going to see all those properties through some protocols, first on the paper, and then we will use it in the tool. So about basic principles of protocols. So assume that we want to build a protocol for B to send a message to A, a secret message S. Let's start by protocol 0. The protocol 0 is not very good because, of course, B just sends to A its his identity and the secret in clear. Of course, this is easy to attack by an intruder because the intruder can just intercept the message, so A never receive it, and of course this is in clear, so it can obtain S. So let's do better. So let's continue with protocol 1. So in protocol 1, B sends to A B S ciphered by KA. So this protocol is better because if KA and the ciphering algorithm are robust, then A is the only guy that is able to read S. So the expected first property is that S is secret, but the problem is that S cannot be authenticated. So A has no way to know if this message has been sent by B. In particular, it can be attacked by an intruder. So I can impersonate B and send a message to A where he says, "I am B," and this is a secret that the intruder can generate by himself. And this is possible because the key KA is public. And so after this message, so A is going to receive the message, accept it, and then the secret SI is known by I and accepted by A as sent by B. So let's do better. So in protocol 2, B sends to A his identity and is signed the secret S by the private key KB -1. For this protocol, the good thing is that S is authenticated by A as built by B, because the only person that owns KB-1 is B. So the only person that is able to do this, to build this message, is B. So the message is authenticated, but it is not secret, of course, because an intruder can do the following thing: is going to intercept the message, so A is never going to receive it, and since the key KB is public, it can decrypt this and obtain the message in clear, the secret S in clear. Let's do better. So we can do something that is a little bit more complicated and not very good, but let's do it anyway. We were going to use the two things we used before. So we're going to put the identity, the secret, we're going to sign it using KB-1 and encrypt it using KA. So now the expected properties are the following. S is going to be secret because it is protected by the public key KA, and it is authenticated by A because it is signed. This is the good things. These are the good things, the good properties. The problem is that now the intruder can make A accept S again using message replay. So, for instance, here, this is the first session of the protocol between B and A. The intruder is going to store this message, and when he wants, so for instance 3 years later, is going to send the message acting as B. He sends exactly the same message, and A has no way to know that this message is not fresh. So the message is not fresh, and what we say in fact is that A cannot authenticate B, so A has no way to know if B is present here during this protocol session or not. So let's do better. So final protocol is protocol 4 with secrecy, the two authentications, and freshness. So what is going to be done here is that A starts the protocol. So it's going to generate a fresh random number, what we call a nonce. So it generates a number, NA, and sends it to B. And this is also what we call a challenge from A to B. So A sends to B its identity. He says, well, this message is for B. Here is my random number, and then it's encrypted using KB. In fact, the only person that is able to read this number is B, the agent B. So in fact, any person that if A receive back the nonce and NA, he knows that B is present and has decrypted this message. So the second message is just B saying to A, you are A, I am B, here is your nonce, and here is the secret message. And this is the answer of B to the challenge. So the expected properties are that S is secret, the nonce here is fresh, and so is this message. It is authenticated, and so finally A can authenticate B when he received this message. Of course, you can do the same thing with symmetric keys. You've got the same challenge, but the message are just encrypted using KAB. So now we are close to using the verification tool. What we're going to formalize and verify. So what we're going to look for are logical attacks, which means attacks not on cryptography nor on the implementation of the protocols, but only on the protocol logic, so the mechanics of the protocol itself. And we're going to do this in the Dolev-Yao model, where you model both the protocol logic and some intruder capabilities. And the assumptions that are made are the following. So first, the cryptography is secure, which means that an intruder cannot decrypt a message if he doesn't know the key, and he cannot also guess secret keys or nonces. And the other assumption is that the intruder has a strong and complete control over the network, which means that he can start any number of parallel protocol sessions. He knows all the public data of the protocol, so public keys, public values, and he has all the privilege and keys of the corrupted agents, which means that there are a number of corrupted agents that share their private keys, for instance, with the intruder, and he can read, store, block every sent message. He can build and send his own messages, and he can compose or decompose messages, and he can encrypt and decrypt if he has a key. So let's go on formalization of protocols using SPAN and AVISPA. First, a few things. So the problem is that you cannot use the notation we had until now for protocols, which is called the Alice and Bob notation, because it is too ambiguous for rigorous formalization. So for instance, here an example that we will see in the following using SPAN and AVISPA is if you use this notation and you think about protocol 4 we designed just before. In fact, on those two messages you've got the NA value, which is the nonce, but it has not the same status between the two messages, because in this message it was generated by A, and here it is different, because when A received this message is going to check if this nonce NA is the same as the one that he has sent here. So it's not exactly the same status, but in this notation it has the same syntactic form. So it's a problem. That's why all formal tools use languages to avoid these kind of problems. Usually they use either description by role using process calculi like ProVerif and AVISPA and Citer. So AVISPA is the one that we're going to use. But you also have some description by rules, just like Tamarin, that is going to use rewriting rules. So let's go on formalization of protocols. So now we're going to use VirtualBox to load the SPAN and AVISPA tool. So let's go to VirtualBox. There we're going to import an application, and it should be in the download folder you have. So in French it's téléchargement, sorry for that. And so you can use the OVA file that has been downloaded. So just open it, continue, import. It takes a few seconds. Okay, so now it is here. It's called SPAN Ubuntu 10.10 Lite. So let's start it. And remove those things. Yep, sorry. So now we can use the full screen. It will be better for us. Okay, so we've got the full screen now, and so this is a SPAN, the SPAN virtual machine. So you've got some documentation if you're interested here in this folder, some manuals and so on. Here we're going to use files in the RECI tutorial folder. So let's just look at it. So here is the RECI tutorial folder where you have basic protocols. Let's go and open the protocol 0 file. So here you've got the description. Oh, there is a small mistake, but it's going to be corrected. So this is a comment, and here you've got the description of the protocol. So it is described role by role. So you've got here role A, role B, etc. So let's start by role B, because B initiates the protocol. So here what you have is that B, he knows B himself, okay? He knows agent A, he knows the secret S, and he knows some two channels. Two $YAO channels. So one which is called SND for send, and one that is called RCV for receive. Then you've got here below a local variable which is called state, which is going to be a natural number. It is initialized with value 0. And there is a transition here saying, so here you've got the arrow of the transition, and these are the precondition for doing the transition, and this is postcondition. So for the transition to occur, you need to be in state 0 and to receive start. So start is a specific message that is sent by AVISPA to start the protocols. And when it is true, then you go to a different state. So here it says state prime, which takes the value 1. And in AVISPA or HLPSL files, when you've got a variable x, x prime means the new value for x. So here, in fact, during this transition, you've got the two values of states. So state is 0 and state prime is 1. So you can access to both values. But each time that you generate a new value for a variable, it is stored in the state prime value. It's the new current value. And there is another property here, which is a secrecy property. So what it says is that S is supposed to be a secret, a shared secret between A and B. And this is just a label saying that this property is going to be called sec1. This is role B. Here you've got role A. A knows himself. He knows agent B. He knows also some channels. It has the state value, and it has a local variable S, because at the beginning A doesn't know the secret S. So it's a local variable. It's not in the role. Initially state is 0. And so if it is 0, and if A received a message where you've got the identity of B, which is exactly the one that was sent in the role, and a text that he does not know, which is S. So that's why here it's an S prime, because it just receives the new value for S. Then he moves to value state, for the new value for state, which is 1. In this file, there is another important section, which is the session section, where you say for an agent A, an agent B, and an S, how you compose the two roles to have a valid session of the protocol. So it just said, well, you have got to have a role B in parallel with a role A. Okay. And finally, you've got the environment section, where you define some constants. So here you've got the Alice and Bob constants, which are agents. Here you got a public key that has nothing to do here, so just remove it. It's a mistake. It's not important, but it's clear if we remove it. You've got constants for Alice and Bob, and you've got a text, S1, which is going to be the secret, and sec1, which is a label used for labeling the property. Here we got another interesting thing, which is the intruder knowledge. So initially the intruder only knows Alice and Bob. And then you say what kind of verification scenario you're going to run. So here we just run a scenario where you've got one session between Alice and Bob and the secret S1. And finally, the goal section, which says what kind of property we want to prove on this specification, which is here sec1, so the secrecy property. So now let's go back to the desktop and launch the SPAN tool. So here we're going to load the HLPSL file, which is the proto0 file. So we just open on the desktop the RECI tutorial, basic protocol, and proto0 HLPSL. So we find the specification we just have seen in the editor. So what we can do now is just to launch some verification tool. So there are in fact 4 different verification tools in AVISPA. So you can just select one. For instance, you can select ATSE, and you can execute it, and it says, well, protocol is unsafe. So below you will find the attack trace, which is in ASCII, but we're going to see it in a more graphical way later. What you can do also here is to load again the HLPSL file, and you can simulate the protocol. So if you do this, you're going to animate and simulate the specification, and what you see here is that you're going to build a message sequence chart between Alice, which is playing role A, and Bob, which is going to play role B. And for the moment there is no message between the two, but you can trigger it here. So here there is a message between B and A, and the message is BS. So if you trigger, the message is sent with the values we had in the specification, which is Bob for the identity of B, and the secret S1, which was the value of S. Okay, so if we go back here and we run the verification tool, it says that the protocol is unsafe, which means that we can also build the attack here. And the attack is the one that, of course, we have found before. For this protocol 0, which is just the fact that A never received the message, it is intercepted by the intruder, because here S1 is in clear, and so the intruder, you can check that he can read it. So this is the intruder knowledge, so we can read S1. Okay, so let's go to another protocol. So we can go to protocol 1. So this one is a little bit more stronger, because remind that we're just going to protect the message BS by the public key A. So with regard to the specification, there are only few differences. The first one is that in the roles you will find here the public key KA, and the message are going to be protected by KA. So if you find the brackets and the fact that it is ciphered by KA. So you've got this in the reception and the same in the emission. Okay. And another difference, of course, is that it appears here in the session. Of course, you've got to send this key to role B and role A. And in the environment section, you've got Alice and Bob. You've got this public key, and of course it is used here in the session, and more interesting, it is also in the intruder knowledge. The public key KA is given to the intruder, of course. Okay, and the goal property is the same as before. So let's go to SPAN. We open this second protocol, Proto 1. We execute it, and this one is safe, of course. With regard to secrecy, this protocol is safe because there are no way for the intruder to obtain this value in clear. Okay, but we have seen that the problem with this protocol is that the message were not authenticated. So let's go and see how we define message authentication in the Proto1 out file. So it's the same protocol, except that we have added some security properties. Here, in fact, for authentication, defining the properties is a little bit more difficult, because for secrecy, you just say, well, this message has to be secret. For authentication, you have to say who is going to be authenticated by who. The first thing is that A wants to authenticate this value. So we say here that W request is for weak request, weak authentication. So A wants to authenticate the message S prime, and he says that it is supposed to be built by B. And again, we have got a label for this property, which is here out1. And in the role A, you've got the opposite, which says that B hopes that this message S will be authenticated, and it is done using the label witness. Okay, there are nothing much different, except in the goal where you say, well, we want to prove weak authentication on Auth 1. Okay, let's go. We go back to SPAN and open this protocol, one weak authentication. And now if we execute the verification tool, the protocol isn't safe. And if we do attack simulation, we find the attack that we have found before, which says that B never sends a message. The message is sent by the intruder, who says, I am Bob, and this is a secret that I generate for you. So it's var S1 generated by the intruder, and it's ciphered by key KA. And this is possible, of course, because the intruder knows Bob, and he knows KA, and he can generate this secret. Okay. Oh, we could do the same on Proto 2 and so on, but let's go directly to Proto 3. So recall that Proto 3 is just this protocol where we signed message S by KB-1 and we ciphered the full thing with KA. And so if we look at what is going to be done in the rows, so we now have the two public key K and KB in the two rows, and here you've got the message where you send this, where there is S that is ciphered by the inverse of KB, so KB-1. We know that this protocol permits to authenticate the message. So since S is ciphered by KB-1, we know that it has been built by B. So here we're going to check if it permits to authenticate the agent B. So to be sure that this message has been sent by B now. So the only difference is that here we're going to do the same witness. We say that B is going to check if B is going to send some information for A to authenticate him, and he hopes that S will be enough to authenticate him. And in the role of A is going to do not a weak request but a request. So A is going to authenticate B on S prime. Okay? And so we go there. The goal session is not weak authentication but authentication, strong authentication. And here for the moment we have two sessions, but I'm going to comment one just to simulate the protocol. So here we have only one session between Alice, Bob, a secret S1 and KA and KB. So let's go to SPAN, open protocol 3. Okay, so we can simulate the protocol and see that the message that is going to be sent is Bob S1 ciphered by the inverse of KB and then ciphered by KA. Okay, and so with one session, recall that this protocol is safe. Okay, but if I go back to Proto 3, I just add another session, so I can do a replay. Now I go back to SPAN. I click on View HLPSL in order to reload the file, so you can check that it has been reloaded. Here you got the two sessions, and you execute it. Now it isn't safe, and we can see what is the attack, and the attack is this one. Oh, sorry, I've started two screens. So here you've got this situation. You've got a session here between A and B and another session between A and B. And here you can see that A has received a message that was not sent by B. So he has accepted a message as coming from B. And in fact, this message is just the message that was sent by B in the first session of the protocol. Okay, so we found just the same attack as before, as we have seen on the paper before. So now let's just quickly go to Proto 4. So Proto 4 is this protocol where you've got the agent A that sends a nonce, and the agent B that sends it back and with the secret. So the way it is going to be defined is the following. So here you've got an additional variable, which is the nonce NA, and this is going to be used here. Initially the value is 0. A receives the start value, then it goes to the state value 1, and it generates a new random number NA. And he sends what? He sends A, B, NA prime, which is the new value that it just generated, and the full message ciphered by KB. And then, of course, B is going to receive this. He receives a value NA prime because he doesn't know NA, so he received NA prime. And what he does, is it just send back NA prime and adds the secret. And finally, A receives his identity, the identity of B, and here he receives NA and not NA prime because he knows the value of NA and he wants to check if it's the same. But he receives a secrecy S prime that he does not know yet. That's why it's an S prime here. And with regard to authentication, the difference is that, in fact, here B is going to prove his identity using NA prime because he's going to send back NA prime. So it's a proof that he is B. So that's why the witness here is B, wants to be authenticated by A and by sending NA prime. And the request, of course, is just A, B, and on NA, because here the old value of the nonce is NA. Okay? So let's go to the session. So for the moment we have 2 sessions, but again, let's comment one. Go to SPAN, open Proto 4, and we can simulate it. So here we've got the first message. So you can see that the nonce that was generated was, for the moment, the value nonce 1, and B can answer the challenge and sends back nonce 1 and a secret S1. Okay. And in fact now the protocol is safe, but we can even add another session here. So I did it in the editor, go back to SPAN, download again the specification and execute it, and it is still safe. Okay, now we're going to define a simple protocol using SPAN and AVISPA. The objective of this part is to show how we can take advantage of animation to debug a specification. So we're going to design a very simple key exchange protocol where there are 3 agents, A, B, and a trusted third party T. And A and T are going to share a symmetric key, KAT. B and T are going to share a symmetric key, KBT. And the objective of this protocol is to establish a symmetric session key KAB shared by A and B. So if you are in this, initially we are in this situation, and the objective is to establish KAB. And the purpose of this section is to show how to specify protocol and properties, but in fact we have almost already seen all the techniques. But the interesting thing for me is to show how to debug specification using animation. Then we will see that we can also strengthen the protocol using attack discovery. And another thing that is very interesting in my opinion is that we're going to be able to tune and optimize the protocol once it is safe. Okay, so let's go back to the VirtualBox machine. So we're just going to remove all those protocols and open in the RESI tutorial folder the key exchange section. So key exchange 0 is not interesting, and you're going to open key exchange 1. So this is the protocol that is defined in this section. So it's very simple protocol. You see, A is going to send to T a key. It generates a key KAB and is going to cipher it with the shared symmetric key KAT. And then T receives this. He can decrypt because he has got key KAT, and then he cipher it with KBT and sends it to B. And so in the roles, of course, A has got a symmetric key, and T has got the two symmetric keys KAT and KBT, and B has only KBT, of course. Okay? And in the session, we've got this, a role, we put in parallel the role A and the role B and the role T. And in the environment, I've got one session between Alice, Bob, and the trusted third party, that is another agent, and some keys KAT, KBT. So if we go back to SPAN and we open the HLPSAL file, so we move to the RESI tutorial example, key exchange, and we take key exchange 1. So if we launch SPAN, the protocol is claimed to be safe. The problem that it is not. The problem here is that the specification is bugged. And so here, in fact, the specification is syntactically correct, so it's accepted by AVISPA, but it is bugged, it's not executable, the protocol cannot be run. So in fact it is the safest protocol that may exist, because it's a protocol where no message is exchanged, so it's very safe. And that's exactly what says AVISPA. And there is no way to make a difference between a safe protocol and a bugged protocol in a way. You have the same problems in most of the verification tools you have for cryptographic protocols. It's also the case in a way for a proof assistant, for instance, but the difference is that in proof assistance you can just try to execute a specification if it's executable, and you may find that there are some problems. Here you don't have this solution. So it is very wrong here, in fact, because so the protocol here is just sending in role A, you just send KAB ciphered by KAT. So here you can see in the role that you generate a new KAB using the new. You send KAB prime ciphered by KAT, and you say that KAB prime is supposed to be secret between A, B, and T. But the protocol is very unsafe, because here you see that we send in clear the key KAB prime. But again, if we go back into SPAN, so on this protocol, it is claimed to be safe. Now we're going to take advantage of all the other tools we have here to find the bugs in the specification and to figure out when the specification is correct. So we can just try to simulate this protocol. And what we see here is that, in fact, there are roles, but no message can be exchanged. And the first message was between A and T. And so this means that there is a problem either in the role of A that fails into preparing the message, or into the role of T that is not able to receive the message. Now we have to see in which situation we are. That's why we're going to use intruder simulation. The difference with intruder simulation is now that we have an intruder that is able to receive any message that is sent. In particular here, no message can be received or sent, which means that in fact the message prepared by A is not sent. So we can go back to the key exchange specification. Oh, sorry. We can go back to the key exchange specification and see what is the problem. So we know that the problem now is in role A because the message is not sent. So let's have a look. So we have the two variables for the state and for the key KAB. And here, initially the variable is state is initialized to 0. And here we say if we are in state 1 and we receive start, then we do something. The problem is that, of course, this cannot be true. So we just correct. We start at state 0. So it's an error that occurs when you copy and paste many parts of the specification. It's a typical kind of error you have. So we have saved the specification. Okay. And we go back to SPAN. We click on View HLPSL to reload the specification. You can see here that it has been corrected. Now we can try to simulate. Again, it is blocked. But if we go to intruder simulation, we see that now the message can be sent. So the message in which we are interested is this one. So if it is the key generated by A that is ciphered by KAT and sent to T, but T cannot receive it. And here you've got the other message, that is the buggy message we had in the specification and that we are going to remove. The problem, we are going to remove this, but the problem is that T is not able to receive this. Okay, so we go back here, we just remove this, which was incorrect, and we go into the role T. And so in the role T, we see that T is an agent, A is an agent, B an agent, KAB, KAT, KBT, and we've got a state, we've got a symmetric key. Initially the state is 0, and when it is 0 and we receive KAB prime KAT, which is correct, because KAT is a key that is known by T, and KAB prime is a new key that we received, so it's okay. Then we move to state prime, and we send KAB prime ciphered by KBT. Okay, so this is correct. So the problem is not here. We can use another trick, and we can go to intruder simulation. We send at least one message, and we're going to monitor the variables of T. So we do variable monitoring for T, and we select all the variables, for instance. And now there is a small pink rectangle that appeared here. We can click on it and look at the variables of the role. So T is the trusted agent, A is Alice, B is Bob, KAT is KBT. So this is a mistake, because of course the value of KAT should be the constant KAT. So it's a problem where in fact the initialization of the role itself is wrong, and the role is initialized in the session section. So we can go to the session, we can go to the session section. We go to the session section here. Just have a look on how the role T is initialized. So we give to T T, A, B, and here we have KBT, KBT. So it's a problem. It should be here KAT. So we correct, we save, we go back to SPAN, we load again, and now we simulate, and now the first message is exchanged. We can send it. So SK1 ciphered by KAT is sent to T. But the second message is not sent, so we still have a problem on this. We go again to intruder simulation. So the first message, this one, and we see that the second message can be sent. So it can be sent by T, but it is not accepted by B. No way to accept it. It's only the intruder that can read it. So there is a problem in the receiving part of the role B. We go back to the specification and go to B. So B, an agent, he knows a symmetric key, and here what we say is that we received KAB KBT, and the problem is here that KBT is known, that's correct, but KAB is not known. It should be a KAB prime because it's a new value that we receive from the network. So we save, correct and save, go back to SPAN, load, simulate, and this time we have the 2 transitions. So it's okay now. In fact, when we click on execute, the protocol is safe, and that's correct. Okay. In fact, this protocol is not correct as soon as you add a session. But a session between Alice and the intruder, where there is still a trusted agent, and the session key between Alice and trusted is K80, and the session key between the intruder and the trusted agent is K80. And of course we have to define here K80 as a symmetric key, and of course the intruder knows these keys. It's a compromised key in a way. If we go back to SPAN, we reload this file and execute it. Now it's unsafe, and the attack that is found is the following. So here you see that there is a session between in fact Alice and the terminal and the intruder, in fact, and you've got the session between A, B, and T. And here Alice generates a new session key SK1 that should be private for Alice, Bob, and terminal. And you see that in the end this session key is sent to the intruder using the symmetric key KIT. And you see that in the intruder knowledge, in the end, this session key is here. Okay? So this is the attack. Okay. Now we could walk across different protocols, but we're going to go directly to key exchange 5. Sorry. So key exchange 5 is an interesting protocol. There's the typical protocol that your students may write. I mean, there are so many securities that it is safe in the end. We're going to check this, but it is safe. But there are identities everywhere, nonces everywhere, and so on. So it's very big and complex protocol. Our objective is here to have a protocol where there is secrecy and there is mutual authentication of A and B. Okay? But it is clearly not optimized. But if we load it in SPAN, so we use kexchange5, we can execute and it's safe. And you can check that the verification scenario are quite no, for the moment it's not that difficult, but we're going to add sessions. For the moment there is only one session, but if you uncomment this, there are 2 parallel sessions between Alice and Bob, and another session between the intruder and Bob, and another session between Alice and the intruder. So we put all those sessions in parallel, and if we check, this protocol is safe. But now there is an interesting point. Now if you want to optimize, to tune it, to simplify it, how are you going to proceed? The problem is here that you want to keep safe. So what you're going to do is just to remove some parts in the messages to check if it is still safe. So for instance, we're going just to remove the first identity here because it will make a smaller message. So it's between role A and B. So it's the last message of A. We can remove the A last message. So here, remove here. Okay, and we're going to so it's role B, and here we receive A and we remove it. Okay, and we save. Okay, I didn't do it. Okay, and so we go back to SPAN, view the protocol, and we can check that it is still safe. So we know that we can safely remove this, and the protocol keeps safe. In fact, we can do the same for some time, but and remove some other things. So I just put an optimized version of this protocol, and you can see the difference between the two. So this was the original one, and now this is a simplified one, where in fact I've even removed one nonce and some identities. And if you go to SPAN, you can open it and check. So it's kExchange 6, and check that it is safe. Another thing that is interesting is that you can try to remove some of the components of the message, and each time you will have an attack. So it's some kind of smallest protocol you can have for this kind of property you want here. Okay, so it's nearly over now. So we've done this, and so just to conclude, I will just go on some other examples. So I remove this. I will download them directly in a SPAN. So in the tutorial you will have some other examples in this directory. So this is a Needham-Schroeder public key protocol, and these are credit card protocols. So CB-B0 is the original protocol that was used with credit smart cards. Maybe the simplest thing I can do is just to show you a simulation. So in fact, I will just comment this session. So it's a protocol where you have a user, the terminal on which you're going to type your PIN, and the credit card. And initially the protocol is the following: the card, so the terminal reads on the card some information. So the information for this card, which is called the card 1. So you've got data 1 and some signature of the bank. Then the terminal asks for the PIN. The user type its PIN. So in fact, it's the code is typed on a separate device, which is supposed not to be read by the intruder. So that's why it's protected here by the shared symmetric key. And finally, the PIN is sent. The PIN code, sorry, is sent to the card. And if it's correct, the card says OK. What is interesting is that on this simple specification, if you put 2 sessions with a different user, the same terminal, a different card, with a different data and a different code, well, in fact, there is an attack, and the attack is this one. So in this attack, in fact, what you can see is that the credit card 2 is going to be used on terminal here, this one, not on this one, but on this one. And the code that is going to be typed is code 1. So the credit card 2 is going to be used using the code 1. So it's very, in fact, this simple attack is the one that was used some time ago in France on an attack on credit card by Serge Humpich. And so here you also have the DDA. So this is the EMV protocol, the DDA version, where you have the same protocol but that has been corrected, and we use it on the same way using 2 sessions, and this time this one is safe. Okay, and you've got another session, another simulation where you got a valid credit card, you've got a valid credit card, a valid terminal, and a yes card, which means a smart card that answers anything that you're interested in, anything that you want, whatever the PIN that is typed on this card. And so here the protocol, so the protocol is not very interesting. What is interesting is the attack that is found. This is the attack. So in fact, you see that this card is going to be accepted and used here in on the terminal, but the code has never been typed. It has been, in fact, replaced by some agreement sent by the yes card. Okay. Okay. So thank you. Have fun using SPAN. On the VirtualBox machine, you have some information if you're interested in having the password and so on. There is some documentation here, and there is some other tutorial here, where in particular you have some other format, which is called the CAS plus format. So I can just show you how it looks like. So SPAN comes with another format, which is CAS plus. I can open some example here in the tutorial. So I will open simple protocol. So it's a format that is based on the Alice-Bob notation. Okay, so here you've got the specification. You can also specify some scenario for the verification. Here I've got 2 sessions here. Okay, though there are a lot of comments, but the specification is rather small. And the interesting part is that it's going to generate automatically some HLPSL. So it's only to have a shorter way to write specifications. In particular, the verification labels have to be moved or written by hand. It's better, but it can give you a first skeleton of the specification. Okay, it's over. Thank you for listening, and if you're interested in also in tweaking a little bit the machine, there is some information about the machine here in the SPAN and AVISPA tutorial. Okay, thank you. Bye bye.